gonna go stand over here.
You're always fine. All right, good evening, everyone. My name is Sam Nasser, and this is the Cleveland C# VB.NET user group. We meet here once a month, typically every fourth Thursday. Meetings are free of charge and open to the public. And as you might have guessed by the URL down at the bottom, that's where you can find all meeting information for both past, present, as well as future meetings. The meetings are free of charge and open to the public, and we discuss everything related to .NET. And next slide, please.
It is the next slide.
Some overhead information. The meeting space is courtesy of Tech Systems. They've been a proud sponsor of the group for over a year now. And the drinks and pop over in the corner are courtesy of iNeato. And we have some prizes that are courtesy of Post Shop that we'll be raffling off later, which will include a Post Shop license as well as a Starbucks gift card. Also, web hosting and video recordings courtesy of NIS Technologies. Some general information. Sorry, the slide just somehow didn't come through.
My bad, sorry.
But the Wi-Fi password is ROC 3001. You want to look for the ROC network, either the 2.5 gigahertz or the 5 gigahertz. And the password is 3001. Excuse me, ROC 3001. Restrooms, if needed, are all the way down at the end of the hallway on the right-hand side. And last but not least, please know that participation is encouraged. So at any point in time, jump in with questions, comments, and also please put your cell phones on vibrate. Tonight's presenter is Guy Royse, the gentleman to my left, and he will be talking about machine learning for gamers. Guy is a developer from the Columbus area, and he comes to us tonight. He's been flying all over, and he managed to squeeze us into the schedule between Boston and New York. And sometime you'll make it over to Columbus again, I'm sure.
Yeah, Sunday I'll be back home.
Sunday, very good. So without further ado, I will turn it over to Guy.
Thanks. Bitter patter of applause. So I'm trying to figure out what's making the screen blink on us. Maybe if I don't move. I'm like if I jump, I'm afraid it's going to move. I'm sure it's just like those connections aren't real strong or something. So, anyhow, oh yeah, this is the About Me slide. This is my title slide. So my talk tonight is called Machine Learning for Gamers, Dungeon Forecast and Dragon Regressions. And so what it is it's a talk about machine learning for people who know nothing about machine learning. So if you're a developer and you hear all this buzz about machine learning and you sort of come into it and you have this idea that, well, I'll just upload a bunch of data and it does magic. And that's your level of knowledge. This is intended to educate you on machine learning, the types of problems you can solve with machine learning. I put this talk together because I found, I worked for Nexosis in Columbus starting like last August. I started with Nexosis. And we have a developer-based machine learning product. And I'm like, hey, developers, you can put machine learning in your app. It's really easy. And no one knew what to use it for. And this is kind of because we're developers, right? So I've been writing software since, the early 90s. And my entire career, I've always had to teach myself things. So developers aren't afraid of learning new things. That's part of the job, right? But developers are always looking for how to do things, right? It's like, hey, I'm learning the latest new language or the latest new JavaScript framework because the one from last week is dated. And so I need to get up to speed, but so I need to learn Python, let's say, or I want to learn, then move this way and it doesn't move.
A little bit more.
Okay.
Each time you sway, it clicks on.
Oh, really?
Yeah, it was.
That's wow. So as developers, we're focused on how, not what. So when we're learning a new programming language, we're not asking what does it do. We ask how does it work. And like, maybe I'll do this. How's that? Is that better? So we're asking how, not what. That's great. We all know what a programming language is for. It's for writing programs, right? And if we're looking at a web framework, we all know what a web framework's for. It's for, building a web app. And so the question isn't what is this thing for? The question is how do I use it? How do I make it build web apps? But then we go to machine learning, and it doesn't work like the other things we've looked at before. It's different. But we get on Stack Overflow and we ask all these how questions, and then they all get downvoted, and it becomes a giant dumpster fire. Well, more of a giant dumpster fire. And that's unfair to Stack Overflow, honestly. There's a lot of great stuff out there. And you all know that if you're on Stack Overflow, you don't accept the first answer that's been approved and it's at the top of the list. There's a better answer hiding underneath it. So always read all the answers. And so anyhow, what I found is that developers didn't know what machine learning was for, and they were trying to figure out how to use it. And so I thought I'd put a talk together on what machine learning does and how you might put that into your application. And so there's like 2 lines of code in this entire talk. A lot of pictures, a lot of charts and tables and things explaining how it works, but there's no code of consequence. So that's me. If you want to tweet at me while I'm talking and distract me, that'd be fantastic. There's my GitHub account. A lot of the code for many of my talks and the slides are available on there. The slides for this talk are not available on GitHub, but they are. You can find them on my website. And I work for DataRobot. I mentioned that I worked for Nexosis. We were purchased by DataRobot back in April, and so now I work for DataRobot, but I'm doing the same thing. So this is a Dungeons & Dragons themed talk, so I got feedback saying that I should have a character sheet. And so this is my character sheet. I thought Bard was probably the closest class to map to sort of what a developer evangelist does, because I can do lots of different things, but in any real scenario where things matter, I'm useless. I'm obviously a dwarf. I think that just goes without saying. I threw myself as level 5. I haven't been a developer evangelist very long. Made myself neutral good because I thought that seemed legit. But the important thing here is my abilities. Strength 10, Dex 8, Con 12. We don't care about the physical attributes of a developer. But the intelligence and wisdom there are both 8s because I don't actually have any knowledge. But I'm very charismatic, which is why I stand in front of people and talk. So I have 16 there. Which means that this talk will be all substance and no style. Oh wait, all style, no substance. So. Also, another thing about me is this right here. Any guesses to what that might stand for? If you can see it.
I am not a data scientist.
Ding. I'm not a data scientist. If you have deep data science questions, is anyone here a data scientist? Good. I say that because if you are, you'd be bored. This is telling you what machine learning does. If you're a data scientist, you know that already. I'm not, but if you want to get deep into the technical details of data science, and it's like you pick this particular algorithm with these particular hyperparameters and blah, 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 blah. I'm not going to be able to answer that question because I'm not a data scientist. That's not my strength. I understand machine learning from a developer perspective, but I'm not a deep expert on machine learning. But I think machine learning is kind of like Dungeons & Dragons. Now, before I go any further, I got an important question to ask as well. How many people here have played Dungeons & Dragons? Oh, tough crowd. Yeah. There's 2 ways that question could go. Either you get a few people and I'm like, oh God. Or you get a whole bunch of people and then I'm like, oh, thank God. So I think machine learning is kind of like Dungeons and Dragons because it's got a lot of weird jargon, right? So people who play Dungeons and Dragons will talk about their hit points, their armor class, their FACO. You're really old school. In machine learning, people talk about neural networks and support vector machines and gradient descent and all these terms. And in D&D, the person's talking about these terms, and they're really, really excited, even though you have no idea what they're talking about. And in machine learning, everyone's using these terms, and they're really, really excited, even though you have no idea what they're talking about. And there's a lot of weird tools that go with it too. If you look at these unusual dice here, I don't even know. I'm a gamer, and I don't even know what some of them do. You've got this weird roulette wheel type thing over there, and one of the dice is rock, paper, scissors, lizard, Spock. And machine learning's got a lot of tools that are really unfamiliar as well. How many of you are Python developers or have done anything in Python? Yeah. So if you haven't done Python, Python is kind of different from other languages. It's a little weird. Kind of like that little spinny thing over there. So I'll start out with the obligatory "what is machine learning" slide, and say that my one-sentence elevator answer to what is machine learning is to say that it's math at scale. So a lot of machine learning is math that we've known how to do for decades, if not longer, but that we've never been able to scale up to anything useful. But now we have a crap ton of GPUs, and we can just amp that thing up, and all of a sudden, even a basic linear regression can be run with 10,000 variables, and we can do that. Whereas before, that was too computationally expensive, so we wouldn't do things like that. And so it's just amping up math at a level that we haven't been able to run before. That's sort of my pocket handy quick definition of machine learning. And it's kind of why we're talking about the topic at all nowadays. So you always kind of wonder, well, why couldn't we do this before? And we've always known this math. The answer is because our math knowledge and finally our compute capabilities intersected to make a new thing possible. And then all of a sudden everyone's excited about doing this thing.
What does that do for us?
What's it do?
Yeah.
That's what this entire talk is about.
What can you apply for me? Apply to me.
So it allows me to predict things. So I can take a bunch of variables and then make predictions based on other related variables. The most common example would be a house. A real common example would be evaluating the value of a house. You've got a lot of variables that determine the value of the house. Its neighborhood, its square footage, its condition, whether it's got a basement or not, how many bedrooms it has, how many bathrooms, whether there's a pool or not, so that the value can go down, stuff like that. And you can give tons and tons of examples to a machine learning algorithm. It'll build a model using those examples. And then we can then put in houses it hasn't seen and then predict the value of a house it hasn't seen before. Yeah.
Question for you. So when you're scaling these algorithms up, how do you account for unpredictability in the variable? So for example, I work in insurance, right? So
Yeah.
a bunch of variables go into a bunch of stuff that I don't even understand, right? But all of the time there's a lot of things that go wrong. So your predictability is anything but linear a lot of times. And so actuaries build models that kind of factor that stuff in, but sometimes they don't get it right all the time. So what could something like this buy you that would still account for some of those unpredictability, snafus, things like that?
Well, ultimately, it's kind of doing what we do.
Okay.
And so that's always going to be a certain problem to a certain degree, right?
Right.
So part of that is the features you select. All the variables that go into that value of a house. Maybe you're missing one that is influential. But even in that scenario, if you were to plot out the value of a house, you're going to get a band of points. And if you try and draw a line, that line is going to be down the middle of that band. And so there's always going to be some that are off, right? There's always going to be, I think you always got a few outliers. The big value that it's bringing is that this is automated. So the machine's doing it instead of a person. And so that's one of the big things is if you're trying to estimate the value of a house, it's kind of doing what people do, right? We're going to look at all these factors in the house, compare it to comparable houses, and say, that house is probably worth about $173,500. However, it can take into a lot more variables into account than a human can, and so it tends to be more accurate, although it's only as good as the data you get, right? If you train a machine learning model with a bunch of data that's biased, you're going to get a model that makes biased decisions. So, just like people. Few definitions here. Artificial intelligence. So we've all heard the term artificial intelligence. And most of us, when we hear it, we think AI, we think cyborg, we think Arnold Schwarzenegger, we think HAL 9000, we think things like that. And the reason for that is because artificial intelligence isn't a super technical term. It's more of a cultural term. It's kind of like the word planet. So Pluto was a planet, and then it wasn't. And the reason Pluto wasn't a planet anymore is because planet was a technical term, right? They realized this doesn't, they learned more about the nature of the solar system, and then Pluto matched other types of objects more than it matched planets. But everyone else was like, no, Pluto's a planet. Because the word planet, for most people, means those 9 things that we were told planets were when we were a kid. And so it had a cultural definition, a colloquial definition, and a technical definition. So the same words being used for 2 purposes. And AI kind of has that thing going on. We tend to think of it as thinking machines, autonomous robots, who you can have, C-3PO is artificially intelligent. That's what we tend to think of when we think AI. Probably the best working technical definition for AI would be processes that mimic human cognitive capabilities. So you can do that in a lot of different ways. Machine learning is one way that you can do that. You can mimic the sort of cognitive processes that humans have. With machine learning, it's that math at scale thing that I was talking about earlier, where we just give it a bunch of data and it learns from those examples, and then you can use it to make predictions off of those. Deep learning is probably a term you've heard as well. Deep learning is a specialized version of machine learning, and specifically it's a specialized type of neural network. And neural networks are a bunch of connected nodes that are together, and you can have shallow networks where you just have an input layer and an output layer, and you can have networks that have many layers in between, so they're deep. And deep learning is particularly useful for things like image recognition and text-to-speech and that kind of stuff. We're going to be talking about the blue wedge in the middle. Now, that previous picture is how a lot of people are. Machine learning is a type of AI, and deep learning is a type of machine learning. But I kind of like this version here a little bit better. So you see here is on the right, I've got these green circles with different colored fillings. And some of them are blue, and some of them are purple, and some of them are gray. And so the idea here is that the purple ones, we could do some sort of AI application, some automated cognitive mimicking of humans by using deep learning. We could also do that by using machine learning. But sometimes we can actually get away with those sorts of things with just some basic heuristics. So, a series of well-placed if statements can mimic the behavior we need. So AI doesn't necessarily have to mean machine learning. There are other ways you can do it. You can get that same sort of process. So it's another way to think about it. Yeah. So there's 3 basic steps when you're going to do machine learning. You can prepare your data. You need to prepare your data. So that means taking your data set that you've got, all the rows and columns, just tabular data, just like you pull out of a database. And you need to clean it, prep it, fill in missing values, get rid of rows that aren't terribly meaningful. Maybe you got some outliers there that are going to throw the model off. Or you've just got nulls in your data, stuff like that. You prep it, you clean it, you select features that are relevant. Once you've got that data, you can use it to build a model. So you select an algorithm, you set the hyperparameters on that algorithm, and then you build a model. Then you use that model to make predictions. We'll talk about preparing the data first. Some things that you need to understand when you're preparing your data, to understand about the data that you use to train a machine learning model. There's 2 types of data. There's target. That's the thing you want to predict. That'd be one of the columns. And then there's features. And those are things that affect the thing you want to predict, which are all the other columns. A lot of that data will need to be encoded. Sometimes you've got categorical data. So you've got, now let's use a D&D example. You got dragons. The dragons are different colors, right? And so that would be a category. Or maybe you've got some Booleans in your code, you need to convert them to a number somehow. You've got text, you're doing some sort of natural language processing, you need to turn that into some sort of meaningful numeric representation of that. And then you also need to impute your data, which is coming up with reasonable defaults for the missing values. So I like to use the example of temperature. So sometimes we got temperature versus sales. So if you get like daily sales, listed daily sales, and one day you don't have an entry for your sales, 0 is a pretty reasonable default there. I didn't have any sales, that's why there's no data there. However, if I'm recording the temperature every day, and it's 75, and then it's 76, and then it's 36 because we're in Ohio, and then all of a sudden you don't have an entry for a temperature, 0 is probably not an appropriate default. And so you can impute default values in different ways. You can take an average, you can use 0, you can take the mode or the median, whatever makes sense for the problem you're doing. So, but imputation is just guessing methodically. So encoding, here's a couple examples of encoding. Here we've got a Boolean encoding. We got a field in our data set that say whether this monster is a goblinoid or not. It can be a yes or no. And so we turn those into a 1 or a 0. I know, amazing, right? I mean, everyone who's been programming has known this for a long time, and sometimes you don't have to do that if you're doing like decision trees. You can deal with Boolean just fine. You can deal with categories pretty well too. Another type is one-hot encoding. So here's the dragon color that I mentioned earlier. So you can see the dragon color, we got black, blue, green, red, and white. And so what we do, if you look there on the right, is we put a 1 in the column. We create a column for every unique value of every category. And then we put a 1 in the column that matches, and we put a 0 on the rest. And so we put a 1 in the column that's hot, which is why it's called one-hot encoding. And so this is a way of, in essence, sort of turning it into a series of Booleans saying, is this dragon black? Yes or no. Is this dragon blue? Yes or no. And then we can use it to do machine learning. Once we've got all our data where we want it, we got it all encoded, we got it all cleaned, we can build a model.
So do most of the models require the data to be encoded? So if it's some text form, it has to be converted to a numeric form?
Yeah, I'd say most. I mean, usually text is going to fall into 2 categories. It's either going to be some sort of NLP text type of thing, in which case there's very specialized. There's a lot of different specialized ways of doing that I'm not super familiar with. The other option is if it's just a category, then you just want to encode it. And a lot of the libraries have tools built in to do that. So like scikit-learn has a label generator where you can say, well, here's my labels, give me numbers. Here's my numbers, give me the labels back. But it is a step you need to do. You might turn your data, like your literal physical text file, your CSV file, may say red, green, blue, black, and white. But you'll have code that'll turn it into a binary representation of that, one-hot code representation of that, and then it'll feed that into the algorithms to build the model. So here's a small sampling of some algorithms you can use. A decision tree is kind of a flowchart on steroids. So it's basically, you go down the tree and say, is my value greater than 55? Yes, okay, go here. Is this dragon red? Yes, go here. No, go here instead. And then at the leaves of that tree, at the ends of those trees, you have your prediction. And you can actually take these decision trees and create a lot of different randomly generated ones and adjust those values during the training process. You get forests of them, so they call it, they call them random forests. So instead of having one decision tree might be really, really good at predicting the gold piece value of a dragon's horde if it's a red dragon, but it does poorly for the others, and so you can average out the results of all the trees. You've got linear regression. This is a basic one that if we've had any math at all in college, we probably have done, where you're just trying to find that line along a data set And here, I mentioned earlier that you end up with a band of data and you want to draw that line down the middle of it. This is kind of showing that idea there. And then there's a couple outliers that are just there, because you always have a few outliers. Some of those are, if we're looking at housing examples, it'd be, well, that house sold for $1. Well, that's an outlier because, someone gave someone else their house, right? That's not data we want to use to predict the value of the house. And linear regression is usually really good for predicting numeric values. Support vector machine is a classification technique where you're basically trying to draw a line between two groups of data. And if it's on one side, it's one class, and if it's on the other side, it's another class. You can draw multiple lines to do this. I have not implemented one of these myself. I just know that that's how they work. Neural networks are things that sort of mimic how the human brain works. I have implemented neural networks. And you've got this red layer there is a bunch of input nodes. And then the blue nodes are a couple layers of hidden layers. And what happens is you put numbers in the front, and then those numbers are changed when they go into the next node, and they're changed when they go into the next node, and they're changed in the output node, and then you give you an answer. And they're trained by adjusting the weights, how important the output of each of those nodes are into the next set of nodes. And so neural networks are particularly good for things like images, image classification, and those sorts of problems. They're kind of exciting. Everyone gets excited about neural networks because it has the word neuron in it, and they're like, oh, so it thinks. No. It's actually not that much like a human brain. Yeah.
So when you talk about the weight within the neural network, what influences that, and is it more like a dynamic process?
So the way you calculate the weights on the neural networks is they use a technique called backpropagation, and it's using a bunch of really hard calculus that I don't understand to basically figure out which node was more wrong and then adjust the weights accordingly. And you're trying to find that sweet spot at the bottom of your curve.
Okay.
It's called gradient descent, and you're just trying to find that perfect value there, and it works its way through it. I've used it to train image classification for characters on my MacBook here. And I had about 500 inputs of data, 500 characters of input to train it, and I got about a 92% accuracy out of it, which I thought was pretty good, honestly. And I could build the model in like 60 seconds on my MacBook. It's amazing. Yes?
So when neural network, so you're saying a neural networking would be more, you consider more of a calculation thing instead of a thinking thing, huh?
Yeah, yeah.
More advanced capabilities of calculating unknown variables in accounting for unknown variables, huh?
That's correct, yeah. It doesn't think. It just,
Takes effect.
once we've trained it, it's fixed. It's static. It doesn't change. And then we just put values in and values come out. It doesn't.
But it can take in unknown new variables and things like that if you program it to, huh?
I'm sorry?
But it can't, if you need to, you can program it to take in new variables if it needs to, huh?
Yeah, if you learn more data, then you can add that data to your data set and retrain the neural network. It's really just figuring out all the values of the numbers. They sort of cascade like spreadsheets in a way. When you change one number in a spreadsheet and they all recalculate, you're changing the 3 input numbers there, and then it just like goes through it like they just all click through there and recalculate down through the nodes, and then you get output values. They're hard for us to reason about because the number of connections get to be large numbers quickly, and so there's a lot. You can't pull one apart easily and understand exactly what's going on, not because it's not knowable, but because we just can't keep all those things in our short-term memory to understand it. So they're a little hard to reason about in that sense. So sometimes they'll do things and we're like, why did you do that? It's like, probably because of this. Yeah.
So then if you can't really kind of understand it, then what do you use to test the accuracy of that? What's your oracle for that?
So the way you do that is when you set your data aside, and I got a slide coming about this actually, is you say, like I have the 500 characters I used to recognize. I used 400 of them randomly selected to train it, and I used 100 of it to validate its results.
Okay.
And so you set aside some of your data, you hold some of it back, and use that to train it. And actually, I think that's what this is here. So our data is divided up into train and test portions. And so, like I said, it's just rows of columns. This isn't real data, obviously. And so here you get 80% of your data as training data. You use that to train your model. And then use 20% to then validate the training. That's a real common way, common ratio. You could train it with all your data, but then you're asking it to tell you things you already told it, which could lead to your model being overfit. It just memorized all the answers. It didn't figure out where the line was. It just figured out where all the points were at. Yeah.
Does your platform automate the training and testing?
Yes, it does. Yes, thank you for asking. There's actually another way you can do it here, where you can do a thing called cross-validation. If you don't have a lot of data, sometimes this is useful. We actually, at DataRobot, we do both of these things. So what you can do when you're training is you can take, you divide your data up into 5 groups, and the first 4 are used to train it, and the last one is used for testing. Then you take the yellow one there, the next one down, you use that for validation and train with the other 4. And so it allows you to page over all of your data and verify with the bit that it doesn't know about already. There's a slight risk of overfitting with this, but if you have a small data set, sometimes that's what you have to do to get something meaningful out of it. So it's sort of a go through this 5 times using one of them as the test set and the rest as the train set. And so that's called cross-validation. DataRobot, we actually do both. So we'll take 80% of your data, and then we'll divide that into 16% buckets. So 80, 1/5 of 80. And then we'll do the cross-validation with that. And then you can validate it against your holdout data later. And then if you're really confident in your model, then you can take that holdout data and use that as well. Yeah?
You ever use leave one out, cross-validation? That's where you use all the data.
You do end up using all the data. You're basically making 5 passes.
So in practice, you ever use leave one out, where you only reuse all the data for one line?
Well, that's in essence what this is. What we do is we do a hybrid of both. So we do this technique for 80% of your data and leave 20% alone. So you still have that extra 20% to validate against. Because you don't want your data to be overfit. You don't want to memorize any answers.
So there's a technical means to leave one out. Say you have 80% of your training data, but you leave one example out. That's something you want to work on, check on.
Okay.
So say, for example, there's 80 rows of data. Use 79 of them to train your model, and then check one of them to see if it fits before you even define the text it fits. I was wondering if you ever see that in practice. It's rare because it requires so much computation.
I have not seen that in practice, but I'll go back to my original slide. So I'm not a deep expert on these topics. That is totally a question that I have to ask one of the data scientists, whether that's important or not. They've got the statistics background to really understand that. My sense is that it seems like it'd be more risky for overfitting, but I don't actually know that. That's what my guess is. So after you've done all this testing and training and building and validating and everything, you're going to get your model out, and it's going to suck. And there's lots of reasons why it might suck. This is an iterative process. So you get your data the way you want it, you build your model, and then you validate your model and you don't like the results. So then you're like, well, maybe my data is not good, or maybe I picked the wrong algorithm. So we'll change some of those things. Some common reasons you might have bad models could be target leakage. So the target, as you remember, is the thing we want to predict. A leaky feature is a thing that's actually part of the thing you want to predict. So the example I always like to use is if you are trying to predict the power output of a windmill, and one of your variables is the voltage coming out off of that generator, and one of your features is the current coming off of that generator, then you're doing math the hard way. You don't need machine learning, you just need multiplication. Because power is current times voltage, right? Those are terrible features. They're going to highly, highly correlate because they're part of it. And so that's the thing to watch out for. If you get all your features, you build your model, and then your features are ranked on how much of an impact they had on the targets. And you got one that's just like ranked all the way up to 11, and the rest of them are really tiny. You probably have a leaky feature, or a target leakage. So that those are, and maybe not. Maybe that's just a strong indicator, but it's something to watch out for. The other thing you can get is you can get overfitting. I talked about this a little bit earlier. The model on the left is fit because it's got that band of data and it's found the pattern of the data, the flow, the direction of the data. And so it's not going to be 100% accurate for everything you test it against, because you've got this band of data coming up. If these are like housing values, but it's going to be in the right direction. And the other one over there is trying to hit every single point on the line, and so it's memorized all the answers. And so if you give it something it doesn't know, it's just like cramming for a test. Right? You cram for a test, you know all the answers, you put them down, you forget them 3 days later. This guy has memorized everything, but it doesn't actually understand the pattern. So you want what's on the left good, right bad, right? So once you've gone through the cycle of building a few models and you've got a model you're happy with, then you can actually use it to make predictions. How this works differently for lots of different platforms. But in essence, as a programmer, it's going to look something like this. You're going to have a model that you've built, you're going to help predict, and you're going to pass in your features. So in the case of the housing value example I gave earlier, your feature, you would put in the house is this many square feet, it has a basement, it's in this zip code, it's got this much acreage, all those features that are impacted by your house, and that will tell you then, it'll give you a dollar amount. So that's, in practice, what it does. The example I just gave you is actually one of regression, where you're predicting numbers. You can predict classes as well. And actually, we've got 5 types of machine learning I'm going to talk about here tonight. We've got regression, classification, anomaly detection, forecasting, and impact analysis. But before I do that, I have a joke. What's a pirate's favorite programming language? You might think it'd be R maybe, but his first love be the C. So regression. So I've got a regression problem here. We're going to determine the value of a dragon's hoard in gold pieces based on the age of that dragon, its color, and its hit points. So here's the stuff we need to know about dragons for this problem. Dragons have ages: wormling, young, adult, and ancient. They've got colors. There's black, blue, green, red, and white, brass, bronze, copper, gold, and silver. Now, both of these are good indicators for the value of a dragon's hoard. The age of a dragon, the older the dragon is, A, the more time it's had to accumulate gold, and B, the more powerful it is as it ages, so the ease of which it can get gold increases. Color is also an indicator of how much gold a dragon would have. The dragons on the left, are chromatic dragons. They're colors, the rainbow, and they're all evil. And so an evil dragon is more likely to just take someone's gold, whereas the metallic dragons on the right are all good, and so they're less likely to just steal gold from you. And they have varying power levels. Red dragons are very powerful, gold dragons are very powerful. White dragons are kind of dumb. Black dragons are particularly cool in D&D mythos. Bronze dragons, I don't remember what bronze dragons are like. But they have different qualities about them that might affect the amount of wealth that they've accumulated. Hit points, that's how much damage you have to do to a dragon to kill it, is going to have a bearing on how much gold that dragon can accumulate, because if you go as an adventurer and say, I'm going to go slay the dragon and get the gold, and he's got a lot of hit points, then you're going to die, and your gold will be added to the dragon's hoard. And so, dragon's harder to kill, dragon's going to have more gold. The hoard value is just the total value of the dragon's hoard in gold pieces. So your data would look something like this. You'd have a lot more of them. I actually used my D&D books to do this. I went through and I took my Dungeons and Dragons books to work, which I've never actually been able to legitimately do that. It was fantastic. And I sat down with dice and I rolled all these. Okay, I got a young gold dragon, this and I rolled them all up with different treasure hoard values to make this slot. So it's got verisimilitude. But this is what your data would look like. You got a categorical field over there, the age, that have to be one-hot encoded, right? You got the color of the dragon, which would also need to be one-hot encoded. You've got the hit points, which is a number already, so it's good to go. And then you've got your hoard value. And you probably have thousands of these, maybe hundreds. Maybe tens of thousands, it depends on, given this number of variables, I would think hundreds would be fine. Maybe a couple thousand would be plenty to build a meaningful model.
So the more features you have, the more your sample has to be?
Yeah, generally. Unless the features tend to correlate strongly. Like if, young dragons are copper, and, ancient dragons are always red, then you really don't have two features, right? You have one feature. And there's actually other ways, tricks you can do for encoding this data. Like you can take the hit points and say, you can put them in ranges. So if it's got between 0 and 50 hit points, and 50 and 100 hit points, and we probably all filled out surveys that work this way. What's your age? They could ask you a number, or they could say, are you between 30 and 39? No, I'm not. And they call that bucketing. So it's another way of taking numeric data and actually grouping it in a more meaningful way. Bucketing. So you put it in buckets, right? Your data in buckets. And so this is what your data would potentially look like. And with that data, then you could go ahead and make a prediction. You could provide the age, the color, and hit points of a dragon, which is hard to get. Hey, Mr. Dragon, how many hit points do you have? Breathe fire, you die. But you provide those three values, and then it'll spit out the hoard value. So that's what machine learning does. You provide all those features, you get the value out. You can also build a model that does this. It'd be a different model, but you could predict the hit points of the dragon based on its hoard value, and its age and its color. They'd be different models, but you're predicting, just a different. You said this is a feature in my data set. No, I want that to be a target and make the other thing a feature. So you're just predicting a different thing. And it's pretty easy to do. They're both numbers, but it does sort of beg a question: is could I predict the color of a dragon using this technique, or could I predict the age of the dragon? Instead of a numeric thing, could I predict a categorical thing? And the answer is yes, but. Because that's what classification is. It's the same thing, except the thing you want to predict is a category. And from the algorithm's point of view, they're different. Right? You use certain algorithms for classification, you use certain algorithms for predicting these numbers. But from an end user point of view, hey, I want to predict a category, or do I want to predict a number? And so predicting a category is called classification, and predicting a number is called regression. And so I have a classification problem here that I call literal classification. And the problem we're going to solve is based on the 6 key abilities and race of a character, determine what class would be best to play. So if I've got a strength of 10 and a dexterity of 14 and an intelligence of 3, and I want to play an orc, what class would be best for me to play?
Mage.
Absolutely. I was going to go with Bard. The intelligence of 3 mage. It wouldn't even work. The jerk mage. So here's some of my characters. So they've got 6 key ability scores. These are numbers usually in the range of 3 to 18. Because traditionally you rolled 3 6-sided dice to generate them, and 18 was the highest you could roll on 3 6-sided dice. It's not how it works anymore, but back in my day. And your abilities are strength, dexterity, constitution, intelligence, wisdom, and charisma. And different classes need different abilities. If you're, if you're playing Conan the Barbarian, you probably need to be strong. You probably need to be able to take a lot of damage, so you have a high constitution. If you want to play, a cleric, they require a higher wisdom score. If you want to play a wizard, high intelligence, or high charisma.
What happened to the assassin?
They're still there, actually. They're in 5th edition as a, what do they call it, a particular path that you can take in your character, so they're like a variant on the road. So, 3rd edition had them. I don't know if 4th edition did, no one played that. Yeah, different abilities, they're suitable for different classes. So that's totally a reasonable input into the type of character you would want to play. The race you want to play, some races have ability bonuses baked into them. So dwarves have a higher constitution, half-orcs tend to be a lot stronger. And then the class then is the thing we want to predict, right? So I got these abilities, I want to play a dwarf, what class should I play? I will say that Tiefling and Dragonborn are not my favorites because they're new, and I've been playing D&D since the 80s, and I have campaign worlds that I built back since then. They don't work with them. It's like you got this world full of humanoids, and then there's just like half dragon character walking along, and everyone's like, what? It's weird. But that's information about the characters, right? Here's what your data would look like. We got our ability scores there. We got a race. We got a class. And again, we would probably have thousands of these. Now, one assumption about this data is that all of these sample characters are decent, right? If we made a database full of really lousy picks, and this is random, so some of these may be lousy, then it's going to give us lousy results. If we make a database that says you got an intelligence of 3, you should totally play a wizard. And if that's their input data, then our model is going to say you should play a wizard because it's learning from the examples. So the assumption here is that this data is probably actual characters that people have played and were serious about. Because the player's going to, you're going to go through and you're going to look at the rules. You're going to say, I want to play this class, this race with these abilities, because it all works together. And so this data has to be decent. If we have really crappy data, well, it's garbage in, garbage out, right? I mean, it's the oldest saying that I remember learning as a programmer. Then once we have that, then we can go out and we can say, well, I've got these ability scores. Thank you. Maybe if I glower at it.
You could try turning it off and on with that, just turn it on and leave it.
Yeah. Oh, that's what I've been doing the whole time, didn't you know?
So I put it out like this and have us all squid.
Yeah. So anyhow, you put in your 6 ability scores there, right? You put in the race you want to play, and it'll spit out a class. Now, depending on your algorithm, it may just spit out and say, you should play a barbarian. Decision trees tend to do that. However, others, like random forests, would give you several possible outputs and score them. And you might think these would be percentages, and they can be if you use certain techniques, but they don't have to be. So they're just a meaningful score in the context of all the other scores. So they're only really meaningful relative to each other. And in this case, we've got a high strength dex and con. So first choice is half orc. For half orc, first choice is barbarian. The next choice would be bard because the charisma's kind of high, and the rest of them are made up because obviously wisdom 9 would be a terrible cleric. So, but it's showing, and I like that it gives you those scores. I actually prefer those sorts of outputs because it gives you a sense of how confident the model was. If you got, the barbarian, like you can see bard and cleric, they're fairly close. And so you get a sense, it's like, you can pick either of these as a second choice. It just gives you a little extra data as to what's going on there. And again, you could also build a model that would predict which race you should play based on the class you want to play. Be a separate model, but it's, you know, you can do the same sort of thing, because it's just you're predicting a categorical column. So both of the types of machine learning I've talked about so far are what we call supervised machine learning, which is to say that we know the answers. So we've got a bunch of data, and we've got a thing that we know that that's that thing. So we've got all these ability scores, and we got a race, and we know that that particular example should have the output of this class. We have all the information about a dragon, and we know the output should be this number. So we have an answer to the question we're asking. There is a type of machine learning called unsupervised machine learning. There's two types of common ones, two that I'm aware of. There's anomaly detection and clustering. I'm not going to talk about clustering. I'll talk about it very briefly. I don't have any slides for it. Clustering takes columns of data and finds natural groupings in them. And then tells you, hey, it's like classification when you don't know where the classes are at. And it's kind of like taking your junk drawer and spilling it out on the table and saying, okay, well, this is a thing. Well, this one's kind of like that. Well, this one's kind of like that. Well, no, this is a totally different thing. And just grouping things together. And so it's finding those sort of when you dump that drawer out, you don't know that you've got 4 categories of things, and which one is it? You're just grouping them into logically grouped things. And then you're done and say, I need to buy a little organizing tray for my drawer so that now I know how many slots I need, right? That's what clustering does. Anomaly detection finds outliers in your data. And there's a couple different ways that can work. You can do it through, you can hand it all good data and say, understand this data, and then I'm going to give you more data model that I built off of this. And you tell me whether it's like the data you got before, or if it's different. If it's different, it's anomalous. Or you can say, I'm going to give you a bunch of data. I want you to find the anomalous data in this data set. So there's 2 different ways of approaching that. And loosely speaking here, I'm looking for anomalous characters, because the problem we're going to solve here is, based on your 6, I got a typo on this slide there, how'd that get in there? Based on your 6 key abilities, the race and the class of the character determine if that character is odd, if it's playable, if it's an outlier. Is it a character that people don't tend to play? So you can probably use the same data we used to train the previous model. In fact, it might be useful to run the data from the previous model through anomaly detection first to find weird characters that no one ever plays, and then take them out. And then use them, and then build a classification model using data that's not anomalous. However, you don't necessarily know what the definition of anomalous is going in, because it is unsupervised. You don't know the answer. You're saying, machine, tell me the answer. So here we've got our abilities, our race, and our class. And what we want to do is figure out, I'm calling it a typicality. It's a score of how anomalous it is. And so negative ones are not very anomalous, and positive ones are very anomalous, or vice versa. It depends on the algorithm you're using. I haven't done a lot with anomaly detection myself. I use the Nexosis API to do it, and it spits out negative and positive numbers. I haven't done it through anything like scikit-learn or anything like that yet. It's on my to-do list. So you get these, you get a ranking. And then once you've got that model in place, you can then feed more data into it and say, is this anomalous? Yes or no? Is this anomalous? Yes or no? A good example of something we will use this for would be monitoring servers. So if you've got like CPU utilization, memory, that kind of stuff, and you're looking at server stats, if you feed it a bunch of healthy servers, and then something weird happens, it says you should go check server 1, 2, 3 because it might need some care and attention. Yeah.
Just really quickly, what are your thoughts on the ethics of using like unsupervised algorithms to make decisions that affect people? So for example, this might work very well in a server situation, but let's say you work for a health insurance company and you're trying to figure out whether you should cover a patient or not.
Yeah.
What are your thoughts on that?
I'd say make sure your data is really good. Right? Because if you have biased data, you're going to get biased results, right? I mean, if you're trying to determine whether the likelihood of a prisoner committing recidivism and going back to prison, and you're in one population which gets a lot more trouble from the cops. Your odds of going back are a lot higher, and so then you've got all this data that is confirming an inherent bias in society. And so your data is wrong. Well, but your data is wrong because of everyone's behavior. So that kind of bias can be built in your models, and so you got to be aware of that. A lot of it is just understanding the domain that you're working with. I think anomaly detection, I would never use anomaly detection for anything like that, right? Because you don't really know what it's figuring out.
But you have the skill to understand it. And
Right,
what my point is
yeah.
that a lot of people are going to see this and say, ooh, great, another tool, and really not have the skill or the deeper understanding to know when you should apply it and maybe when you shouldn't. So
Yeah, and that's why you need to make sure that, lots of times, my company's product is an automated machine learning platform.
Okay.
And what it does is it sort of automates machine learning so that you can put it in your application without having to know a lot of the details. However, there's an obvious flaw with that model in certain scenarios. If you're just trying to predict, like these examples right here, these are toys, right? That's great. If you're trying to predict something that's not a heavy consequence, but you're trying to determine whether someone has cancer or not, right? And where false positives and false negatives both have a huge consequence, right? If you get a false positive that you have cancer, congratulations, you're getting chemo, but you don't need it. If you get a false negative on cancer, congratulations, you're dead, right? I mean, those are enormously, those are huge deals. And so it's like, well, let's just use this automated tool and blindly use it. Well, terrible idea, right? Data scientists are needed to do that sort of stuff because they can really understand the data and get to the true meaning of it. And domain knowledge is essential to understand those sorts of things too, where, it's like, yeah, this data's got, this is the data I have, and it's only actually representing half the problem because some of the stuff we just can't get data for, or things like that. And so you want to put more due diligence in building those models. So I don't know if that answers an ethics question per se.
it does. It does. It clarifies.
You need to be mindful of these things, right?
Right.
Yeah.
I just want to point out this. I think it's a really great question because there's already a lot of laws in place that will look for high correlation and collinearity with something that's a protected category.
Yeah.
You just cannot use it as a predictor. You're breaking the law, but you're playing the machine.
Yeah.
So like race, religion, things like that. So if your variable that's being used as a predictor for your model is highly collinear with a protected category, it's just another way of saying that you're going to discriminate. You're going to blame the computer for discrimination because you don't really know. Right?
Yeah.
You just add it into your model, and the model gave you the result.
Yeah, Amazon just had something with us recently where they trained a model that selected male candidates over female candidates for looking at their resumes because their hiring practices reflected that.
Maybe you just couldn't get it big.
Huh?
Maybe you just couldn't get it big.
Yeah. But I mean, so that's a huge issue with data. I mean, if data is biased, the output's going to be biased, right? And there's actually some, in legal areas in particular, sometimes machine learning is just not a possible solution, right? Like what you mentioned, insurance, actuaries, right? You got to be able to say exactly why you're putting things in these different rate categories. And you can say, if your answer to the state of Ohio is, well, the machine just figured it out, they're going to say, wrong answer, right? No, that's not an acceptable answer.
Right.
And making neural networks, for example, a poor choice for those sorts of problems. Now, if you got some sort of basic, mathematical regression model, you can then show these variables correlate to this, and so you can explain it. Then you can certainly use machine learning to do that kind of stuff because you can look at the model and say, oh yeah, this is why the outputs it did. These are how the variables affected it. So it depends on. There's lots of constraints that go into it, right? Actually, DataRobot's got a feature where they'll generate legal text to explain why the model works the way it does that you can use for those sorts of purposes, which is kind of cool. I don't know if it's ever put the test or not. I hope it has, honestly. I don't know, but it is a popular feature. So once you've got this anomalous model, then you can provide it new data and get a measure of how anomalous it is, or find out if it's anomalous or not. I pretty much already said that. Forecasting. This is actually my favorite example. It turns out this could actually be done as a regression problem, but I get cast it as a forecasting problem. And so the idea here is that we want to predict the number of encounters that will be completed at our weekly D&D gaming session, so that I, as the dungeon master, have time to prepare, know how much to prepare. I'm going to base that on how long we're going to be playing, and what players are present. So we've got our date. This is kind of what makes a time series. Makes it forecasting. We're going to provide dates for the future, along with the other values, and we're going to use that to make a prediction. But the date's got lots and lots of data in it, right? The date's got the month of the year, it's got the week of the year, it's got the day of the week. All these things can affect forecasting, right? If it's Friday, pizza sales are probably going to be higher, right? If it's the day after Thanksgiving, all sales are going to be higher, right? So your date can have a lot of bearing on data. This is particularly useful for predicting sales usage. We had one person that wanted to use it to predict call center volumes. So based on how many people are scheduled to be in the call center based on historical call center volumes, and they could look at that date. And that was a factor. Monday at noon, call centers tend to be busy because everyone got a bunch of to-do list items on the weekend, and then I got to call them during the week, and I'll do it over my lunch break, and so they get a bunch of calls. So dates are chock full of things. There's time in there too, right? The hour of the day, noon for the call center, even it being the top of the hour or 15 minutes after the hour tends to be more meaningful than most people schedule meetings the hour or the half hour, but they usually don't schedule them at like 4 or 4. And so if you're trying to predict something along those lines, there's a lot of meaning in the days. Players, that's just who's going to be at this particular game session. The length is how long the session is expected to be in hours. And then encounters is the number of encounters completed for that session. So that would be, we go into the front of the front door of the dungeon and we see a statue, and it turns out it's an animated statue, and we fight it and destroy it until it's just a bunch of gravel. One combat encounter. Then we go down the hall and get through the tomb, and we defeat all the skeletons there. And then we go down another hall, and there's a trap, and we navigate the trap. We get through 3 encounters that night. Productive night of the game. So 3 encounters. That's the idea there. So our data would look something like this. We've got our dates going all the way up to February of 2017 for our weekly games. We've got our 4 players, Alice, Bob, Chuck, and Eve. I always like using Alice and Bob. Everyone, they're like the common 2 characters that are always used in security examples, but it also happens to be my grandparents' names. So it warms me up a little bit. So Alice and Bob. And so you can see here that they're at different times. So in the past, we see our attendance, like on 11/20, Bob wasn't there. On January 1st, only Chuck and Eve were willing to play on New Year's Day. And on the February 5th, everyone was there. Got our length of time spent gaming and the number of encounters. It is arguable that length might be a leaky feature, because if you play longer, you're going to get more done. It might not be the best feature for this data set. I'm not sure, actually. I'd like to have the real data to try this out. This is actually an app I plan on building using DataRobot. And because you can build a custom model for each player, each party, right? I'm running a D&D game, I just keep track every week, and then after some time, I have enough to actually start making some predictions, which would be kind of fun. To ask questions of this model, you just provide future days and future attendance and the amount of time you think you're going to play. So the things for the future, the features, have to be knowable. or at least reasonably knowable, right? So we know that on the 26th of February, Eve is going to be out of town, and so she won't be playing. This is not a 100% guarantee. Bob could get sick. We don't know. We have no way of predicting that, but it's reasonably knowable. The length, we can figure out how much time we want to play. It's just what we schedule. That's also relatively knowable. And then we can use that to predict how many encounters we're going to have. We can also use it to play games. So we could say, well, what if the Chuck wasn't there? Well, how many encounters would we get through? Maybe Chuck talks too much and doesn't remember the rules and makes too many Monty Python jokes and doesn't focus. And so he actually slows the game down. You can find that out using this sort of model. You can put this sort of thing. Hey, ran the model, Chuck, and you're out. Yes, sir.
Okay, so something like that, right, where, Chuck slows down the game. So when you see Chuck, you can assume that there's going to be less encounters. Yeah, that seems like it's kind of more of like a binary one way or the other thing, right? To kind of influence the outcome. So I guess
these are obviously the binary inputs. You could just slow everything down, but not necessarily. You're going to get through stuff, you're just not going to get through as much.
Yeah,
but
he might only slow it down if Bob's there. If Bob's doing the work.
That's a good point.
So
And maybe Chuck and Bob always argue about rules.
So it might seem to be negative, but there's obviously.
But I guess I guess I was using that just because it seems so different from like the date, right? Just because you were saying that how the date's kind of big and one of the important ones. I guess I'm wondering how the algorithms kind of know why a date is important. For example, like let's say you have 212 up there, right? Let's say that's a Thursday. Then let's say the next data point was to the next day on a Friday, right? You can probably assume. Well, I guess I was gonna say you could. It seems like if you're playing on like a Friday, right? You're probably gonna play longer than if you played on a Thursday. If you played on a weekend, longer than a weekday.
Yeah, actually, all my data here is for Fridays, so it's assuming a Friday evening game. but
I guess I'm wondering how the algorithm takes a date as more than a number and actually sees that it's Black Friday, that it's a weekend, that it's a holiday, that it's whatever. Why that ends up working?
It's because you have historical examples where on the third Thursday of every month of the last month or whatever the third Friday it is, you have examples from previous Black Fridays that show the number going down. In this particular example, I don't think the date's actually super meaningful. Like the amount of D&D I get done with doesn't really have much to do with what month it is.
Sure.
And this is probably work just fine as a regression problem. But in the case of like shopping, that you've got historical data that says, like the day of the week is clearly having an effect on my pizza sales. And every week, I've got daily sales and it shows that.
So does that kind of data only really help a lot if it's very complete, like you were saying earlier about the I word, whatever that word?
Imputation.
Right, because I guess, is it more useful to have, for example, like a whole year of dates or a whole week of dates as opposed to kind of cherry-picked examples?
Yes, it's better to have that complete data going back. So in the case of forecasting, the rule of thumb I was given to by a data scientist was you need about twice as much history as you have future. So if you want to predict a year in advance, you need about 2 years of history to be effective there.
Gotcha.
That was the rule of thumb I was given.
Okay.
From one data scientist.
Yeah.
You could probably find a data scientist to disagree with that data scientist.
Okay.
In this case, I don't think date's actually not all that important. And when I implement this for real, I'll probably take data on the month.
Sure.
Because I don't think the month, because you're going to be playing about once a week, it's probably going to be the same night every week. And so really then you're just saying, well, does the week of the year impact how much D&D we get through? Not really. Yeah.
I was just going to say, a lot of these answers, I think, it depends. Like, for example, you talk about shopping, always December is shopping, but then when we use July, it's shopping.
Yeah, I have a Bigfoot data set that shows the number of Bigfoot sightings monthly since about 1900. And it goes up and down and up and down. And it catches the monthly seasonality. So Bigfoot sightings increase during the summer, and they decrease during the winter because big fire rains.
I thought there was more people out.
Yeah, crazy, right? But then you got periods where there's been big growths and everything, and so trying to make forecasting off that data is not really that useful. And the best that when I ran it through the Nexus API, what it always ended up doing was it would just take monthly averages. So it just like all the Januaries in the data set, average them, and said this is what the next January is going to be like. That's all it did. So it found the seasonality of it nicely, but it couldn't find that overall trend line because there weren't any correlating features to help out. And so you get data that's kind of noisy; it's hard to predict things on, right? And July ramping up in sales over history is an example of a cultural trend. That's why you got to update your models periodically. Yeah.
Are these all using the Nexus API or the available option?
I actually haven't built models out of any of these examples. So you could do this with the DataRobot API supports regression, classification, and forecasting. So you could do these. I don't know if we have anomaly detection yet or not. I'm not sure. So. And I know that we don't have the next one. Oh, this is me saying you could also predict length based on the encounters. Impact analysis. So all these techniques that I have on here, we can do with the Nexus API. And it's still live. You can go use it if you want. And, we're not going to shut it down anytime soon. And it's certainly worth playing with. And it's free. So Nexosis. It's spelled Nexo, Nexosis. It's a portmanteau of Nexus and Neosis, like as in diagnosis. So the Greek word for knowledge and the Latin word for intersection. Impact analysis is, I like to call it beforecasting. So what you do is, you know that a thing happened at a certain point in time, and so you take that point in time's data back and you do a forecast. So you're predicting what could have happened or should have happened based on historical data up to a certain point in time, and then you compare it against what actually happened and see if a thing that happened on that date had an impact or not. So to use a pizza shop example, if your pizza sales, there was a power outage on a particular day, and you want to see what impact that power outage had on your pizza sales, presuming that it would go up because no one has power, so they can't cook, so they order pizza instead. And so you could then take that point in time, make a prediction from there forward, and compare it against your actual sales, and then find out if there was an impact or not. In this case, we're going to predict the impact or measure the impact of switching from Pathfinder to 5th edition. And we're going to use that same data that we use for our how many encounters we get through a session. So here we've got that same data, right? There's Alice, Bob, Chuck, and Eve, my stalwart players, and how much time we spent gaming, number of encounters we got through. But what we can do is we can say that on January 1st, I switched from Pathfinder to 5th edition. And that should be an easier game. It's a little simpler to run. And so I should get more encounters. So I'm asking the question, I know how many encounters I got through in January and February there. How many would I have gotten through if I hadn't switched? And so I tried the dates. And this is just forecasting for a period in the past. The nice thing is that all your features, you know them. So you're not trying to guess what they are. They're not knowable, they're known. And so you can provide all those and you get a number of encounters. And what we find is that we predicted a certain number of encounters. We had an actual number of encounters. And so on the first, we got through 3 encounters. We thought we'd get through 5. And so that suggests that switching to 5th edition actually slowed my game down. I'm not getting as much, we're not getting through as many encounters. And that's consistent across this data. Now this is all made up. I actually think that switching to 5th edition would probably speed things up. Actually, I think switching from gaming systems for the first few weeks would be slower, and then it would ramp up over time. But this is just an example of how you can use forecasting. You can, like I said, with pizza sales, it's really easy to get your head around how that would be useful. So those are our 5 types of machine learning that I talked about today. The Nexus API actually does all of these. DataRobot, we do regression classification and forecasting. I think we do anomaly detection, but I'm not positive. I haven't used the Nexus or the DataRobot API to do that yet. And I know we don't do impact analysis. But I mean, but you could do it yourself manually by just picking the past point forward and then comparing the results yourself. This DataRobot site, if you want to check it out. We don't have any really strong developer-facing tools at the moment. It's more enterprise sales-oriented. But we got a little bit there on the site. The blog's got some good content. And maybe you work for a big company that wants to do something like that. That'd be great too. If you just want to play with machine learning as a developer, I'd recommend checking out the Nexus API. Since we're a wholly owned subsidiary of DataRobot. Any questions? I think everyone asked them during talk, so which is totally cool. Yeah. Yeah.
Do you see any of these techniques applying to
Gosh, I have no idea. I know that there's these AI challenges that people use to play like StarCraft. Is it StarCraft? You were nodding your head vigorously, so.
It's actually everywhere, and you don't even see it because it's so subtle. So, for example, if you're a first-person shooter and you're aiming at something that you're a little bit off, the computer anticipates where you're being in the next 100th of a second or 100th of a second, and it does that with algorithms that you can.
So it's compensating for lag, basically, using predictive models. That's cool. I didn't know that. I'm going to totally use that in another talk. Thank you. Any other questions? Cool. Well, I'm Guy Royse. And feel free to reach out to me online. I got some stickers here if anyone wants them. There's a slide with all the images I stole off the internet. Actually, they were all on Flickr, and they were all allowed commercial use. So. And there is the DataRobot logo. And this is something for Sam to talk about. Thanks.